So the last type that we need to learn is noble gas notation, or sometimes it's called shorthand notation or shortcut notation, all different kinds of things. But basically you're going to like it because you will not have to write so much. You get to write it in a smaller fashion. So when you're doing noble gas notation, a couple of things. First of all, you use the preceding noble gas. You may only use noble gases as your shortcut. In case you don't know, from 8th grade, where the noble gases are, it is group 18, okay, last group on the periodic table, and those are the only ones you can use in this notation. Because sometimes people like just start picking random ones in there, and I'm like, no, you can't do that. Okay, so you have to do the noble gases. But I'm going to show you why you can do the noble gases. So first together, we're going to do the electron configuration for argon. Ready? We start with always 1s2. Then comes 2s2. All together now, 2p6. Y'all are not doing this together. 3s2, thank you, Casey, and 3p6. All right, now let's do calcium. Again, always starting with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now let's do my favorite element, vanadium. Okay, it's got 23. So here we go. 1s2,
2s2, 2p6, 3s2, 3p6, 4s2, 3d3.
Okay, 3d3. You said 10? We're not filling them, we're stopping. We stop when we're done, okay? Now, here's why you get to do noble gas notation. Look at the configuration for argon. It happens to also be the configuration within calcium and also the configuration within vanadium. So we can use that as a shortcut because anything that comes after argon has that configuration in it. So we could actually say argon in brackets, has to be in brackets, 4s2 as a shortcut way to write the configuration for calcium, which is a much nicer way to write it, right? Takes less time. For vanadium, we would write argon in brackets, 4s2, 3d3. So basically, you take the noble gas that comes before the element that you're writing the configuration for, and you put it in brackets, and then you start reading the chart like we've been doing. So argon ends in 3p6, so you just start counting from there. Okay. Once you get to krypton, you start using krypton for your noble gas configuration. So everything in period 4 will use argon. Everything in period 5 is going to use krypton. What is everything in period 6 going to use?
Xenon.
Xenon, including the 4 F's down below. Okay? And then everything in period 7 is going to use radon, including the 5 F's down below. Okay? Because that's where they fit into their period number. Okay? On your worksheet that you've been doing, when you're drawing the orbital diagram or the arrows, okay, if you look at the top, it says for the valence electrons. Okay, these are the valence electrons, the things that come after that noble gas. Those are your valence electrons, so that's what you'll be drawing. So if I was going to draw it for vanadium, I would draw the 4s, draw my arrows, and then I would do the 3D, and then I would stick 3 arrows in there. And that's how I would draw that. Okay? Yes?
If you wanted to find, like, argon, is it cheating to write AR?
Ah, I'm glad you asked that. Yes, it is cheating.
All right.
Yeah. So if you are wanting to find the noble gas configuration of a noble gas, for instance, if we were going to do krypton, you can't just take krypton and throw it in brackets. That's cheating. Okay? But you can take argon and put it in brackets and then do the 4s2, 3d10, 4p6. Then you would start using krypton as your noble gas. Okay, so that, yeah, that gets tried every year. That's cheating. You can't do krypton in brackets is its electron configuration. Okay, not allowed. Okay, so that's how you do the noble gas configuration. Now I need to show you some exceptions to the electron configuration rule, because very few things are 100%, right? There's always an exception to the rule, right? It's the same in chemistry, right? here we go. Here are your exceptions. We already talked about the definitions of octet rule, so I'm going to kind of skip through that. I saved electron configuration, noble gas configuration, until after we practiced it the other way. So now, first of all, A, it would have been too much at one time, and B, you appreciate it a lot more now that we did all the 1s2, 2s2. Now you're like, oh, that's so much easier. You're welcome. Okay, so here are our exceptions. First one we're going to come to is chromium, and the reason it is an exception, you would expect chromium to be 4s2, 3d4 to end, but in actuality it's 4s1, 3d5. And the reason for that is that sublevels are more stable, or actually they're the most stable when they're half full. This is on the very back page of your notes. They are the most stable whenever they are either half full or completely full. Okay? So what it does is they shift those electrons from the energy levels to fill it up halfway or completely full. Okay, not sure where I left off, so let's just say half filled and completely filled shells are more stable, so it shifts them. Okay? So chromium is the first element that we come to that does that. So we would expect it to be 4s2, 3d4, but it's not. It's the 4s1, 3d5 because it's more stable for it to be half filled. Okay? So what's an easy way to remember the ones you got to remember is if you look at chromium, it's everything in their group. Okay? So molybdenum, or as you call it, molybdenum, so you know how to spell it, molybdenum does the same thing, and tungsten does the same thing. Sg is seborgium. We don't care about it. It's man-made. We'll never do anything with it. You can ignore it. Okay? The next group that does that are the ones, well, if we're doing it right before we get half-filled, when do you think the next group is going to do it? Right before it's going to be full. So which one would you guess is it? It's copper. Because copper, we would expect to be 4s2, 3d9, but it goes ahead and fills that D level and does 4s1, 3d10. Okay? So again, the ones that are in that group, copper, silver, and gold, are your exceptions. Okay? You will have to know that for a test. Okay? You will have to know that for a test. So, in addition to gold, silver, and molybdenum, or molybdenum, you got to remember in there the copper and the chromium and the tungsten. Now, there's a bunch of exceptions in the F block. We don't learn those. We ignore those exceptions. We just go with what we're doing. And quite honestly, we don't do a lot. Today, you've got some in the F block, so you can see how they feel. But we just don't do much with they don't react with much stuff, so we're not really dealing with them. As we go through next semester and this semester, you'll see why the electron configuration is important, because it determines whether they're going to gain, lose, or share electrons, which determines how they bond. Okay? With that being said, you can finish working on the worksheet.